todos, para todas. Para nosotros es un placer tener hoy en día a una invitada ilustre, a Yaya Morcopatay, que viene de la Universidad de Montana, de Estados Unidos. Ya, ella estaba acá colaborando con nosotros en el laboratorio de Ciencias del Edificio, Bioscience, junto con la profesora Andrea. Y hoy en día tenemos también la posibilidad de que ustedes tengan a esta invitada relacionada con los temas que estamos tratando en el curso de Proyecto Constructivo. ¿Ya? Voy a hacer una pequeña introducción de su biografía en inglés, ya que ustedes la van a escuchar traducida en sus audífonos. So I'm going to change now to English so you can hear me and then they can hear you in Spanish. So Professor Jaya Mukhopadhyay, she's an associate professor from Montana State University in Bozeman. She's an architect from the University of New Delhi, and she has a PhD from Texas A&M. Her research relates in net zero buildings, building energy simulations, and daylight analysis and energy efficiency in commercial buildings, also in passive buildings, and buildings with high standards. She has a lot of knowledge, and part of her teaching is in building environmental control systems, which talks about high performance, facades, all the conditions.
Hay un problema con la salida de acá, dice. El cable nomás está tomando.
Okay. Should I go over again? Is it working?
I think I can hear you.
Yeah, you can hear me right now.
No, from there. From there.
From there? Okay. There's always technical problems.
Yes. Ahora sí escuchan.
¿Sí? ¿Va todo de nuevo? Yeah. Okay. Borrar y contener.
I can introduce myself.
Yeah. Yeah. Okay. Bueno. So I'm going to introduce Jaya Mukhopadhyay. She's an associate professor from the University of Montana, Bozeman. She's an architect from the University of New Delhi, and she obtained her PhD from Texas A&M. Part of her research is in net zero buildings, daylight analysis, building energy simulations for commercial, as well as passive buildings in general. Part of her teaching focuses in indoor environmental quality, environmental control systems, and she has done a lot of consulting through her lab.
Okay. Please, like near to the computer.
Okay. Okay. And she's basically doing high performance buildings analysis. So I'm going to leave you with her so you can talk about her lecture, Building Performance Evaluation.
Okay, thank you so much, Isa. My name is Jaya Mukhopadhyay, and I usually give extra credits to students who can pronounce my name correctly. So as Isabel said, I'm an associate professor at Montana State University, and it is a rival university of the University of Montana. But I have been working in the United States, working and living in the United States for the past 20 years, but originally I'm from India. I'm also the director of the Integrated Design Lab, and our lab basically provides both energy and daylighting analysis services to both architects and engineers across the state of Montana. So today I will be presenting to all of you my research, which focuses on building performance evaluation. And I have divided my research into 3 parts. In the first part, I will be describing some basic concepts of building performance evaluation. In the second part, I will be talking about application of building performance evaluation to different projects that my students and I and my colleagues have undertaken to inform our design decisions. And in the third part, I will be presenting some case studies showcasing passive design strategies that you can borrow and use in your designs to inform energy efficient operation in your designs, as well as indoor environmental quality in your designs. So I want to begin my presentation by gauging your understanding of building performance evaluation. So the first question I wanted to ask you, and I need translation help here, is what do you understand by building performance evaluation? Any show of hands?
La profesora le está preguntando qué entienden ustedes por evaluación de desempeño de edificios. Que alguien levante la mano.
You can practice your English.
Ya, también los que se atreven pueden hablar en inglés. Vamos, vamos.
Come on, vamos.
Yo les pregunté antes.
Efficiency about the use of energy, illumination. I think it's about that.
See, I think you're on the right track. Yes. Now let's ask you the second question. Why do you need building performance evaluation? And I don't want to put you in a spot, but anyone else wants to answer? Why do you need building performance? Why this talk about building performance evaluation? Any thoughts, ideas, political advice? Vamos. Italo?
Tomás.
Okay. We'll get there. Okay. It's just to get you started to think about building performance evaluation and its importance in your design process. And I've got slides to answer these questions for you. And the third question, which might be easier for you, is how do you conduct building performance evaluation? Any thoughts, ideas? Thomas? Now I know your names.
Doing measures in the building.
Perfecto.
I don't remember the name, but I think it's a kind of fan on the door to measure the infiltration of air.
That's perfect. Yeah.
For example, I know there is more ways to measure, but I know that one.
That's good. So you're thinking on the right track. Yeah. So we're on the right track here. Okay. All right. So to answer the question, what is building performance evaluation? In general terms, as Italo said, it is the process to evaluate the performance of a building to ensure that it operates efficiently and appropriate indoor environmental quality is being maintained. Okay, so we all have ideas of energy efficient operation, right? And now, once again, I would like to have a show of hands is what do you understand by energy efficient operation? When I say energy efficient operation of the building, what do I mean by that? Any thoughts? Any ideas? Okay. So it's basically implementing energy efficiency measures in your buildings. It could be implementing energy efficiency measures for your envelope. It could be introducing passive strategies into your building. It could be introducing high efficiency mechanical systems into your building. And it could be using the renewable energy resources to power your energy consumption. So all this is a whole range of energy efficiency strategies that are available to you. Okay. So now my second question is, what do you understand by indoor environmental quality? And I think Italo, you just touched on it. But can I open this question to other students? Any thoughts? Okay. All right. So IEQ, and I think this might be you might have touched on it with Isabel and Andrea. IEQ can be categorized into 4 categories. And you have indoor air quality. That's this instrument right here that's measuring the indoor air quality or assessing the indoor air quality while I speak. You have lighting and day lighting. You have acoustics, and you have thermal comfort. Now, if you think about it, if you just think about it for a second, there is a relationship between energy efficiency or energy saving strategies on one hand and the resulting indoor environmental quality. Okay? If an engineer gets to design your building, he or she will just design a box, no daylighting, no nothing, but just a box. That doesn't ensure indoor environmental quality. That's why we need both engineers and architects to work together to design both energy efficient buildings that have appropriate indoor environmental quality. Okay? So my point in this slide is that sometimes energy efficiency strategies or energy saving strategies that we implement in our buildings don't go really hand in hand with the resulting indoor environmental quality that you see or get in your buildings. So to answer this question, why we need building performance evaluation. So to put things in context, in the context of this rapidly changing climate that we all are experiencing on a day-to-day basis, let's start with Chile's commitment to carbon neutrality. And sometime back, Chile announced decarbonization of its electric sector to achieve carbon neutrality by the year 2050. Okay, I'm sure all of you are aware of that. So in order to get there, energy efficiency is key. Okay, energy efficiency is key. But as you can see from this graph out here, buildings consume approximately 22% of the total energy consumption in Chile. So for architects and engineers to incorporate energy efficiency in building design and operation is important. But it's also equally important for us to ensure that our occupants in these buildings are comfortable, are healthy, and are productive. Okay, so to ensure that both aspects of building design and operation are addressed, building performance evaluation is key. Okay. So how does building performance evaluation fit into the context of building design process? Okay. So to answer this question, let's take a step back and we have to ask ourselves, what is our prime responsibility as architects? I think our responsibility is to build efficient buildings and is to build comfortable buildings, right? So how do you ensure that? You ensure that by putting your hands, or we have to ensure that as architects, as engineers, we have to put our hands around tangible issues and to start quantifying the impact our design decisions make, both on the environment as well as on the occupants who inhabit our buildings. Okay? So all of a sudden, building performance becomes an objective that is equal to the more traditional items and objectives in the design process, such as cost, such as schedule, such as quality assurance, and concepts such as research, such as simulations, such as calculations, all the fun stuff that you did in your, or you do in your environmental control systems class, all those little things, energy modeling, now become these core problem-solving tools that you can use to analyze data. Okay, and we as architects have to use these tools, and that's why we are encouraging you. I'm sure Isabel, I'm sure Andrea are all encouraging you to use these tools in your design decisions, in your design process, to make your design decisions, to inform your design decisions. Okay. So to answer the question, how to conduct a building performance evaluation, you can use several methods. Okay. So the first one I have up on the slide up here is building performance simulation. Now, there are various types of modeling software that are available to you to conduct simulations. And for example, you have tools to evaluate climate analysis. And I think you have tools to evaluate climate analysis, you conduct climate analysis. There are specialized software that you can use to evaluate different aspects of building performance. And these include things such as evaluating the performance of a building envelope, for example, evaluating the thermal comfort conditions of the spaces that you design, natural ventilation potential of your buildings, daylighting potential of the spaces that you design. And then there are some extremely powerful software programs that are available to you that conduct whole building energy simulations at various stages in the design process. Okay? So these are just some examples that you could use for your building performance evaluation. But mind you, the list is really not complete out here. These are just examples. So here is a graph that highlights the importance of incorporating building simulation tools in the design process. And this curve that you see out here on the slide refers to as the McLeany curve. And it implies that the designers are most efficient with their resources when shifting their efforts upfront in the design process. Okay. So let me explain to you this graph out here. On the x-axis, you will find the different stages of the design process. So you have the pre-design stage where you do your site analysis. You have the schematic design stage, design development stage, construction document stage, and it goes all the way a procurement stage, construction administration stage, operations stage. So these are all the different stages of the design process that you as architects will be involved in. Okay, and on the y-axis, you find effort and effect on building performance and cost. So as you look, if you look at it, in the initial stages, the ease of changing design is high. And the ease of changing your design, how difficult is it to change the orientation of your building if you're designing it on a sheet of paper? Nothing, right? Nothing. Okay, but the ease of changing your design decreases as one progresses in the design process. Now, on the other hand, if you look at it, the cost of making changes to design is low in the initial stages of the design. However, in the later stages of the design, the cost of changes, if made, become very, very high. Okay. So now if looking at the traditional design process, you will find that most of the changes are made in the construction documents phase of the design process. However, if you use building simulation tools such as Cove, such as Sapphira, such as Climate Studio, you tend to make these changes upfront in the schematic design stage or in the design development stage. And as a result, you are reducing the impact on costs and efforts on this project. Okay? So that's the value of using building performance simulation tools upfront in your design process. Okay? So you can also measure how a building performs, and for that you would need instruments such as meters, and I guess there's data loggers out here. So for example, if you want to measure carbon dioxide levels, you can use this particular meter right here. To measure illuminance, you use what is known as a light meter. If you want to measure acoustical performance of a space, you use a sound meter. So these are different measurement tools, instruments, data loggers that are available for you. And while there has been a considerable focus on measuring and regulating resource efficiency, of buildings, there has been very little attention that has been paid to the issue how well the buildings meet their design intents for occupants. Okay, so building occupants such as yourself represent this wealth of information that tells or informs the designers how well the building actually works. And the challenge for the designer is to collect this information and to collect this input in a systematic and a meaningful manner. So you will see this cartoon out here. You will see things like, I don't think this air has moved since 1957. Okay, that's one problem. I can still smell Wally's chili. Okay, that's another problem. So it is exactly these type of behaviors. It's exactly these type of behaviors that you will find in your buildings that result in higher operation costs and that result in higher carbon footprints of your buildings. Okay, and this is all occupant information. Okay, so in order to evaluate occupant behavior in our buildings, we use what are known as post-occupancy evaluation surveys. So here is a little note on one such post-occupancy evaluation survey, and it is known as ROAST. And ROAST has been developed and maintained by Kieran Timberlake, which is an architectural firm based out of Philadelphia, United States. And ROAST lets you assess or evaluate the thermal comfort in a workplace. Okay, and through different questions that are posed by ROAST, it captures and maps occupant feedback onto your building's floor plan and provides you with visual data. And that visual data you can then use to inform your design decisions, and you can identify trends that would inform your design decisions and make informed improvements. So this is the user interface of ROAST. You can see up here, you can access it on your iPhone. And this is the way ROAST tabulates or evaluates the results from this feedback, and it maps it on that feedback onto your building plans. Okay. You can also evaluate the performance of exterior spaces around your buildings. And those spaces are typically used in university campuses and in urban areas. And these spaces also need to be designed and optimized both for use as well as enjoyment. And these spaces do come with their own challenges. For example, you have climate, which can't really be controlled. So that complicates the assessment process. And also, unlike buildings that are occupied by tenants that have a fixed profile associated with them, all sorts of people come and go in these spaces at all sorts of times. And that makes user surveys extremely difficult to control. Now, here is a resource that I have given to you, and hopefully I'll share these slides with you at the end of this presentation. And this resource can help you to evaluate the impact of planting trees in your exterior spaces on the resultant comfort of your occupants. Okay. So building performance evaluation is also extremely important in the green building design process. Okay, so design teams are actually required to conduct a building performance evaluation to demonstrate compliance with these different rating systems that you have out there. So for example, to ensure energy efficient operation, more recent version of LEED and the Living Building Challenge actually requires actual energy performance of building in addition to the simulation or the anticipated or simulated performance of the building. And it has to be demonstrated over a period of 12 months after the occupants have been, or after the occupants occupy the buildings. Okay. So in this next set of slides, I will be showing you examples of different building performance evaluation methods that we use to inform design decisions. So here is a project we did as part of the Green Team at Kirksey. And this is a project for Houston Community College. And this is the Learning Hub and Science Center at the Houston Community College. Now, this project is an example of how daylighting simulation software can be used to effectively inform design decisions. Okay. So just to give you a background, the facility houses a welcome center, it houses a library, it houses certain science laboratories, and it also houses meeting rooms. And the design team conceived the facade to be a billboard that showcases the activities within the building. So all public spaces within the building have a visual connection to the outdoors, as well as views to the rest of the campus. Okay, so that's the facade right there. Now, unfortunately, this billboard facade and this connection to the exterior came with a price. And the main facade, as you can see in this diagram right here, faces the west. And that is because of architectural constraints. So the design team realized that there could be some serious issues with both low angle sun entering the space, as well as glare in the space. So the expertise of the Green Team was sought for, and our task was to conduct daylighting analysis on this main hall of the building and to provide the design team with a feedback for appropriate shading strategies that could be used to create a more comfortable space. So several options were assessed, and two of which I have presented up here. There is an option for how a vertical shading system performs and how a horizontal shading system performs. And we used Radiance program to assess the options and come up with the solutions. Here's another project that one of my students undertook in the year 2017. And this study challenged the criteria of a LEED rating system at that time that addresses the issues of glare. So as part of their responsibility of the integrated design lab, the students were evaluating these buildings that were attempting to comply with LEED. And the buildings seemed to be passing and meeting the LEED criteria for both daylighting and views. But at the same time, we were having numerous complaints about glare in these buildings. And this led us to perform simulations as well as post-occupancy evaluation surveys to survey. We were trying to conduct both simulations and POE surveys of a LEED certified building to actually see what was going on and what was happening in the building, and to use that information to inform criteria used in LEED for certification. Okay. So for this study, we examined Jabs Hall, which is a LEED certified building on the MSU campus, and we assessed the building in terms of its performance with regards to both daylighting and glare. So as part of the study, we compared the results from all the procedures we had to follow to comply with the LEED requirements with independent evaluations of glare using simulations and post-occupancy evaluation surveys. So we concluded that the illuminance simulation option provided in the current version of LEED was not sufficient to adequately address this issue of glare. We recommended the introduction of a glare metric to in the LEED criteria or in the LEED process for complying with the daylighting requirements. We also recommended the mandatory use of annual glare assessment method in the compliance process. So here's a snapshot of the analysis that was conducted for the study. You have a web-based post-occupancy evaluation questionnaire that was developed using Qualtrics software. And this questionnaire was distributed to the faculty and staff of the building and required them to evaluate their overall satisfaction with both the daylighting and glare conditions based on their experience of occupying these spaces for both summer, for spring, and for fall semester. And we also conducted point in time and glare, annual glare analysis. And we found that glare occurred not only from the exposure to the southern sky, but also from mullions, from white walls, from desks, from exterior spaces, from exterior surfaces that surround the windows. So also when we compared annual glare graphs to point-in-time graphs, we found that point-in-time glare rating systems were insufficiently representing a full range of glare conditions. And therefore, the use of these point-in-time graphs could be misleading in understanding the annual glare potential of the space. Now, here is another project that I think could be of interest to you, and this is one of my favorite projects. It is a study on tiny house. Okay, so now for those of you who don't know, the tiny house is this class of residential buildings that is less than 40 square meters or 400 square feet in area. And these type of buildings can be seen as potential models for affordable housing. Okay, so this model of housing can potentially also address the issues of homelessness by providing an option for transitional housing for homeless populations. And the idea is that if you move homeless population to such such models of housing, it can save a lot on healthcare costs, on emergency room services costs, on hospitalization costs incurred by, that are typically incurred by city officials or the agencies that are responsible to address this issue. Okay, so the School of Architecture at MSU is currently working with HRDC, which is Human Resources Development Council, and this is a regional council in Montana that is involved in such activities. And the point here is to provide such units to the homeless populations in Bozeman, Montana. So with all this hype about social advantages of the tiny house, the environmental impact of the tiny house has not yet been scientifically validated. Now, to think of it, the high envelope to floor area ratio of this type of a building, this building type, poses some very unique challenges, both in terms of energy consumption of this building, as well as its resultant impact on the environment, on the indoor environmental quality. Okay. So in this project, in the first leg of this project, we monitored the indoor environmental quality of two such tiny homes that were built in Bozeman. And this is a measurement plan that you can see out here for an off-campus tiny house. And this measurement plan was developed to monitor temperature, humidity, and CO2 levels. And a similar measurement plan was developed for the tiny house constructed on campus. Now, here's a graph that correlates the CO2 levels with outdoor air temperature. This is an XY graph. So you will see on the x-axis, you have the outdoor air temperatures, and you have CO2 levels on the y-axis. So for most of you, you may know that acceptable CO2 levels are at around 1500 parts per million, or ppm. And these standards are provided by ASHRAE Standard 62, which is this universally acceptable standard for ventilation in buildings. Okay. So what you see in the first house is that elevated levels were observed when the outdoor air temperatures dipped. And that informed us that the ventilation system was inadequate for this particular house. Now, on the other hand, in the second house, CO2 levels were independent of the temperature levels, of the outdoor temperature levels. So thermal images were also taken for both the houses on cold winter nights. And these revealed conditions for thermal bridging and infiltration that cannot be typically seen by the naked eye. And these images actually helped us to identify issues with construction that could be improved and in the next iteration of the tiny homes. So this next step of our study was to provide recommendations to improve the design, construction, and operation of tiny homes that would both reduce energy consumption and at the same time ensure appropriate indoor environmental quality. So these different strategies for envelope, ventilation, as well as passive heating and cooling were tested. And the specifications of many of these strategies were adopted from the passive house standards, which I'm sure many of you are familiar with. Now, a calibrated whole building energy simulation model was used to conduct this analysis, and both in terms of energy efficiency as well as how well these strategies or implementation of these strategies were able to meet the indoor environmental conditions of the space. So here you can see some results of the simulation exercise. Okay. So based on these results, we had certain recommendations, and these included the use of construction technologies that provide greater value of insulation and air tightness to these homes. We also recommended the implementation of passive ventilation strategies to address overheating issues that we observed in the first stage of our study. We also recommended minimizing the use of windows and keeping the window sizes to be within 10% of the floor area. And finally, we recommended the use of hybrid passive cooling strategies that would, such as the evaporative cooler, that would address the cooling requirements in the short summer months that we have in Bozeman. Okay. So here's another project where the indoor environmental quality was measured and energy consumption was monitored. And this is a project that has been sponsored by the EPA P3 program. Okay. So the goal here was to evaluate the physical performance of LEED certified green buildings in terms of energy consumption and indoor environmental quality. So for this study, we had teams of engineering students and architectural students that participated in this evaluation process. The engineering students conducted the energy evaluation, while the architecture students conducted the IEQ evaluation of 2 LEED certified dorm buildings that were located on MSU campus. And in order to conduct our evaluation, we used performance measurement protocols published by ASHRAE. Okay. So here is a snapshot of some of the results that were obtained from the measurements. And this is a snapshot of the CO2 levels in 2 dorm rooms located in the 2 buildings that we evaluated. So for building A, which is marked in red, building A has a forced air ventilation system for heating. Okay, so the CO2 levels decreased to a certain point, after which spikes in CO2 levels were observed. Now, it was inferred that occupants keep their windows closed during periods of very cold outdoor air temperatures, but open during moderate outdoor air temperatures. And also during warmer temperatures, the forced air system would shut off, causing these spikes in CO2 levels. Okay, those are the spikes. Now, a totally different trend was observed in building B, which does not have forced air systems, but has baseboards that serve the dorm rooms. So the absence of a forced air system in this particular building, delivering ventilation air to these spaces, caused these major spikes in CO2 levels at all instances of outdoor air temperatures. Okay, so here is a snapshot of the post-occupancy evaluation that was conducted for the two buildings. So in this final leg of presentation, I have prepared some additional slides that I would like to present to you. And the intent here is to give you some ideas of suitable passive design strategies that you can apply in your buildings in order to reduce energy consumption and to improve IEQ. So I would like to share with you three projects. They're not my projects. They are something that I show my students. So one of them is based in India, and two of them are from the United States. And all these projects actually showcase some of these design strategies. Now, before I move on, I would also like to point out that these projects are located in the Northern Hemisphere. So I will be talking about the southern sun, or the southern orientation, as a source for heat, rather than the northern orientation that all of you are familiar in Chile. Okay, so mind you, there is going to be a switch. Okay. Okay. So in this first project is the Druk Padma Karpo School, and this is a net zero energy school that is designed by Arup. I'm sure many of you know Arup, which is an MEP firm. And this school is located in Ladakh, India. Now, to give you a background about Ladakh, Ladakh is a very remote region of my country, and it is located at approximately 10,000 feet, which is 3,000 meters above sea level. And it is on the leeward side of the Great Himalayan and the Great Zanskar ranges. And this makes Ladakh a very arid climate with very intense solar radiation. Now, in other words, the climate is hot and dry in summers and cold and dry in winters. So for this particular project, both the site and the program informed the selection of passive design strategies. So this is a residential school, meaning that students live on the premises of the school in residential building blocks, and this is the plan of the residential building blocks. And these residential building blocks are inhabited at night. Okay? So for the residential building blocks, an indirect passive solar gain system, known as the tram wall, was selected to provide heating for these spaces. Now, the tram wall actually faces the south orientation, and these walls are coated externally with black paint, black heat-absorbing material, and they're also faced with a double layer of glass. Now, the wall gets heated during the day, and the heat gets trapped by the glass, and the heat that is stored in the wall then gets conducted inwards to the dormitories at night. Okay, so that's how a tram wall system works. Okay, so on the other hand, teaching activities occurred during morning hours, right? You have morning classes, teaching occurred during morning hours. So as a result, the designers oriented the teaching spaces 30 degrees away from the south, facing east, facing the southeast orientation. Okay, so now in this building block, the designers use direct solar gain system. And this includes the use of large south-facing windows. And the use of this system actually enables the space to heat up much faster in the morning during class time. And these windows, if you can see, as you can see on the section out here, are strategically shaded to cut off the high summer sun and to admit low winter sun into the space. Now, along with these large south-facing windows, we also have clear stories that work with the south-facing windows to provide natural cross ventilation to these classrooms in the case that these classrooms get overheated. Okay, so it's not, you're not only providing a passive heat, you are not only providing these large south-facing apertures for capturing solar radiation, you're also providing strategies to provide ventilation in case the space gets overheated. So these are some very important concepts that you have to keep in mind when designing passive heating strategies. Here are some more images of the school. Okay, so you can see the classrooms with their clear stories, and then you can see, I think you can see some of the dorm buildings out here. Okay. So in this next example, I want to show you is in Bozeman, Montana, and this is a residential building that has been designed and built by Charles and Marjorie Folks in 1976. And the goal here was to heat this house using renewable energy. Okay, so the sun provides 75% of the space heating needs. And for those of you who are familiar with Bozeman, Montana, it is a cold, harsh climate. Okay, in a few slides, I will show you the temperatures. Give me a minute, okay? So there is no forced air heating in this house. There is no forced air heating in this house. There's just a little stove that provides supplemental heating, okay? So here is a schematic section of the house, and you have a south-facing facade, south-facing glass facade, and the glass admits solar radiation or solar energy during sunny days in winter. And the water in the tubes, and you can see the water tubes out here. This is their living space right here, and you can see the water tubes. So the water in the tubes stores most of this energy. And then you also have like an insulated curtain above the facade. And a thermostat controls that insulated curtain. And that insulated curtain comes down during winter nights, as well as during cloudy days in winters, so as to insulate the house from the cold exteriors. Now, the insulating curtain is left up all summer, and the window is strategically shaded. And also, overheating is not a problem in summers because of the strategic shading of this particular facade. And also, the windows are designed to be operable and opened during warm, sunny days in fall season. So here is a time series plot that shows you the building performance evaluation over a period of 4 days. And you have solar radiation out here. You have exterior temperature, and this is exactly what I was talking to you about, how severe our climate is. This is minus 17 degrees centigrade. This is 32 degrees centigrade. And this is a period of 4 days in winter. Okay, so the temperature hardly rises above 32 degrees Fahrenheit, which is 0 degrees centigrade. Okay. So as this graph indicates, so you have solar radiation out here, you have exterior temperatures out here, you have interior temperatures out here, and you have the water tube temperatures out here. And as this graph, and these are measured, these are all measured temperatures. And as this graph indicates is that the water wall system operating on its own is able to maintain comfortable temperatures within the house. Okay, so that's how effective the passive solar gain system is in Bozeman, Montana. Okay. So in this final slide, I would like to talk a little more about the passive design strategies used at the Visitor Center at Zion National Park, located in Utah, United States. And this is once again a use of a vented drum wall. So as you can see from this diagram right here, during summertime, you have shading over the drum wall that is strategically designed to cut out the summer sun, to shade the drum wall. And during winter, you have this low angle sun that hits the wall that is located behind the glass. Now this wall gets heated and the glass traps the heat in this cavity between the wall and the glass. And the wall then radiates the stored heat to the space that is adjacent to it. Okay. There are also vents located at the top portions and at the bottom portions of the wall, and warm air in the cavity between the glass and the wall rises and it goes into the adjacent space. And then through the lower vent, you have cold air that goes or gets sucked in through the lower vent. And as it meets or as it enters into this cavity between the wall and the glass, it gets heated up and then gets pushed into the adjacent space. With that, I would like to end my presentation. A very special thanks to Andrea and to Isabel and Andrea for inviting me to the University of Concepcion and for all your hospitality. And a very, very special thanks to our students in the box who have been Paula and Amanda, who have been translating this presentation for us. Thank you very much, and I will accept questions just now. Any questions? Comments? See?
I was very interested in the water wall.
See?
You know, do you have more information about that?
Yes, I do. Yes, I do. I have.
It's an, I don't know, it's a circulation system?
No. These are huge, and I have the sizes in my paper.
Yeah.
In the paper that has been published by Charles and Marjorie, and they have written how much what they calculated, how much volume was required to maintain the space conditions of this house. And these are double-storied water walls, and the water is not circulating. The water is, I mean, it is circulating inside, but you don't need to have an active system that circulates the water.
But in some moment you need to renovate the water.
No.
Really?
Since 1976, I asked.
Is it the same water?
Same water since 1976. You don't want to drink it.
Yeah. Okay. Interesting.
Yeah, and I have a video, so when I share the presentation, you will see a video and you will probably hear a little more about what Charles has to say about this in terms of how it's controlled and and how he got hold of these double height water columns. Any other questions?
Pregunten, no
Vamos.
Y no voy a nombrarlo más hacia al azar. ¿Habían visto algún proyecto? Ninguno. ¿De los todos? Qué bien. They haven't seen any projects, so they're all new for them. So that's good.
Muy bien. Any
Ahí hay
questions?
una pregunta.
¿Pregunta? ¿No?
Sí.
Yo, pero
Sí, en español yo traduzco.
Español, and then
es que no me queda claro el sistema del agua. Si es que esa agua se calienta y eso genera como calor para mantener como el interior, o si es como una especie de caldera, como lo que se usa. Y eso como que se puede llevar hacia otros lugares, ese calor.
She doesn't understand how the water works, like the water heating. Does it have like some sort of like a heating pump, or is it just the water, and how does it transfer the heat to the other spaces?
See, it all boils down to understanding specific heat of materials. Yeah. So if you see, water has one of the highest specific heat when compared to other materials that are available to us. Okay, and specific heat is the amount of heat required to raise one unit mass of water through 1 degree centigrade. Right, so it has very high specific heat, and it can be used potentially as a material that absorbs heat, and then it re-radiates that absorbs heat to the space. Excellent question. It deals with the materials or the quality of materials.
Thank you. Sí, lo que tienen que entender son las propiedades de los materiales que decía la profe. Entonces, al tener la capacidad de absorber calor y después de irradiarlo, lo hace de manera pasiva. No necesitas un sistema mecánico para transferir ese calor por conducción, ¿no es cierto? Y radiación hacia el espacio. Buena pregunta, excelente pregunta.
See, you compare specific heat of water, it's 1. You compare it to concrete, it will be 0.75. Some other wood could be 0.5. So they all get reduced, but water is one of the highest. And it has its own challenges. It has its own challenges because how do you store water, right? You can have leaks, you can have all sorts of problems and issues with water. That is why designers usually don't go or opt for water, but it's probably one of the best materials you can use for implementing passive heating strategies. But excellent question. Thank you. Yeah.
That's a nice comparison you just made between the water and concrete.
See.
That is a nice, an easy way to understand the capacity of water.
Yes.
And that is why we have, ella no me escucha, no creo. So, I was referring that it's a very nice comparison, the one that you made between water and concrete, for example. So it's an easy way to understand for us, the capacity of that material.
Yeah.
And that is why we usually see water in our systems here, for example. All the radiators on campus is water. All the solar collectors is water because of that.
Because of that. Because exactly. Okay. It has a very high heat carrying capacity. Yeah, and that's why you tend to use water. And in cold climates, because water freezes, you have an issue right there. So people mix glycol or they mix glycol with water, and that reduces that capacity of heat carrying capacity. But you have to do that because you're protecting the system. This is the variation of the same wall, but now they're using concrete here instead of water because Ladakh is a dry climate, and it's they prefer they're using local material out here. That's why they opted for a local wall, a wall made of local materials. Any other questions? Sí.
Tiene relación con el tema de los muros de agua. O sea, me llama la atención en la casa que está construida en 1970, y cómo se ha podido comprobar un incremento, o sea, ha habido un avance considerable como en los muros de agua que podemos proponer hoy en día. Dice que incluye su localización y cómo se implementa esto, y que se entiende que es un sistema netamente pasivo el que hace como todo el trabajo. Pero hay nuevas tecnologías, nuevos proyectos como para poder reforzar este sistema.
So basically she's asking if there's any new technologies that have been developed from the tram wall system to today, like from basically 1970s to today, that have actually improved the mechanical system itself or passive design?
Yes, that's another very good question. If you've noticed one thing, these walls are really thick. These walls are really thick, and that's to include their thermal mass capabilities. But these days they have phase-changing materials that are much thinner, but do the same job. And I haven't included examples here, but you will find phase-changing materials used in similar walls in greenhouses, for example. And they do exactly the same thing. They're trapped behind a glass facade. They're very thin. Heat gets absorbed. They change their phase. And then when the heat source disappears, they change their phase back. And during that phase, they release that heat. So, and those profiles are much thinner. So yes, you do have phase changing materials that can do these, but they're much expensive and they're still not being tested. I mean, they're being tested, but they're still not in mainstream.
Yeah, they're not massified. Yes. Yeah.
Excellent question. Thank you.
¿Sí entienden lo que es un material que cambia de fases? ¿Sí? Maybe you can explain a little more how the material changes phases, to which phase to another.
This is a question of
As
physics.
simple as saying solid from liquid.
See, so you have a solid material, and then if solar radiation hits it, it changes material from solid to liquid. And that phase, that change of phase, doesn't raise the temperature of the material, but changes its state from solid to liquid. Okay, and all the heat is absorbed for the material to change its phase. Now, when the heat source disappears, the material changes from liquid to solid, and heat now gets rejected, or heat gets rejected from the material because of that change, and hence it works like a trombone. See?
Yeah. Thank you so much. Un ejemplo, la mantequilla, un ejemplo más casero, la miel. Sí, sí. Honey.
Honey, material. Yeah, exactly.
Those are simple examples.
Simple.
Domestic.
Yeah.
Simple examples.
Any other questions? Yes.
Why do you think water walls aren't common to see in buildings now?
Very good question, and I think I did talk to. It's the construction aspect of it. It's the practical aspect of it. How do you store so much of water? What if there is a leak? Water, there's several things that can happen with the construction aspect of a water wall, and that's why people don't really go for them unless they're designing their own homes. So.
Well, in Chile, we have earthquakes, so that adds an even extra.
That could be potentially.
Tenemos terremotos, entonces tener muros con agua, que ocurrió, los edificios en altura que tenían piscina, supieron que se movieron así como tarditas. Entonces, más complejo también. Yeah. Good. Yo creo que ya estamos listos a terminar. Yeah. Thank you so much.
Thank you.
That was a great lecture.
Thank you.
Thank you, Mario.